Hello and Assalamualaikum warahmatullahi wabarakatuh to our lecturer, Teacher Amin, and to all my fellow friends. Today, my partner Badri and I, Zuhilmi, are very excited to present our Year 3 Mathematics Exploration. The title, Equivalent Fraction Discovery Station. Before we move into the activities, let me briefly explain the academic foundation of our lesson. This lesson is fully aligned with the KSSR Mathematics Curriculum. Our focus is under the learning area of numbers and operation, specifically topic 3.0, which is fraction, decimals, and percentage. The target group for this lesson is Year 3 pupil. The main learning standard we focus on is Learning Standard 3.1.2, where pupils are expected to state equivalent fraction for proper fraction with denominators up to 10. So, everything in this lesson is carefully planned to achieve that specific learning outcome. Now, I will move on to the theoretical framework behind our project. To ensure that our discovery stations are meaningful and effective, we base our approach on Jerome Bruner's learning theory with a strong focus on discovery learning. The main idea of this theory is that learning should not be passive. Students should not just sit and listen, but instead actively explore and construct their own understanding. In our Year 3 classroom context, this means we do not simply tell pupils what an equivalent fraction is. Instead, we guide them to discover the concept by themselves through structured activities. According to Bruner, there are three key components that support effective discovery learning, and all three are integrated into our station. First is discovery learning itself. This is the core of our lesson. Pupils actively engage with materials and situations, allowing them to build their own understanding of mathematical values rather than memorizing answers. Second is structure. Although pupils are exploring, the learning is not random. The activities are carefully organized to highlight logical connection between fractions, such as how half is related to 2/4 and 4/8. This structure helps pupils see patterns and relationships clearly. Third is representation, which is especially important for Year 3 pupils. Bruner explained that children understand concepts through concrete experience, visual representation, and finally abstract symbol. In our lesson, pupils start with real objects like pizza slice, move to pictures, and then work with the fraction numbers and symbols. Building on the work of Bruner, this slide explains his three stages of representation, which form the core idea behind how learning should take place. Bruner believed that learning is an active process where pupils construct their new ideas based on what they already know. To support this process, he introduced a step-by-step progression, which we represent here as a staircase with three stages. This helps ensure pupils move smoothly from simple understanding to more abstract thinking. The first stage is the enactive stage. This is the foundation of learning, where pupils learn through physical action and hands-on experience. For our Year 3 pupils, this means handling real objects. As shown on the slide, pupils manipulate concrete materials such as the red clay block to understand the idea of part and wholes in fraction. At this stage, learning happens through doing. Next is the iconic stage. After pupils gain physical experience, we move to visual representation. This stage is symbolized by the icon on the slide. Here, pupils use pictures, diagrams, and models to visualize fraction. And they begin to form mental image, which helps them understand that different visual forms can represent the same fraction value. Finally, we reach the symbolic stage. This is the highest level where pupils work with abstract symbols such as numbers and mathematical equations. For example, the equation 1/2 plus 1/2 equals 1 show that pupils are now able to use mathematical language without relying on physical objects or pictures. To conclude this slide, by following this enactive, iconic, and symbolic flow, we ensure that every pupil experiences a smooth cognitive transition. This approach reduces confusion and builds strong conceptual understanding, especially for young learners learning fraction. That is how Bruner's three stages of representation guide our lesson design.
Okay, now let us move to the next slide, which focus on constructivist learning theory. Okay, first, this theory is closely associated with the work of Jean Piaget, who emphasized that learning happens when learners actively construct understanding through experience and reflection. The core idea of constructivism is that knowledge is not simply just transferred from teacher to student. Instead, students build their own understanding by engaging with tasks, engaging with discussing ideas, and engaging with making sense of what they experience. As shown by the central icon on the slide, as we can see, learning happens through hands-on discovery and collaborative problem solving. There are three main rules and processes from constructivist theory that we have intentionally integrated into our lesson. First, the teachers act as facilitator rather than delivering information through direct lecturing. The teacher guides the learning process. The teacher also provides suitable materials, asks guiding questions, and support students as they explore and discover concepts on their own. Second, we emphasize social interaction and collaboration. Learning is a social process, which especially for young learners. As represented by the speech bubbles on the slides, students are encouraged to share ideas, discuss answers, and work together at each session. Through interaction, they refine their understanding and learn from one another. Third, students are encouraged to reproduce rules on their own. Instead of being given a formula or equivalent fractions, students can discover the rules through repeated experience and repeated observations. By comparing fractions and discussing patterns, they can naturally arrive at correct conclusions. That's it. Thank you. Okay, to further explain the rationale behind our teaching approach, this slide highlights the key principles of constructivism. These principles are strongly influenced by the work of Jean Piaget, who believed that learners actively construct knowledge rather than receive it passively. First principle is active construction. In constructivism, learners are not just empty vessels waiting to be filled with information. Instead, they actually actively interact with their environment. In our lessons, pupils learn fractions by handling materials, comparing parts, and make sense of what they observe through material by hands-on engagement. The second principle is schema theory, which is especially important in mathematics learning. New knowledge does not stand alone. It is connected to existing mental structures or schemas. For year 3 pupils, we build on familiar experiences such as sharing food or dividing objects equally, and then connect this experience to the idea of fractions. As they learn, their schemas gradually develop and become more refined. The third principle is social interaction. Learning is strengthened when pupils interact with others. Through discussion and collaborations, pupils share different perspectives and challenge each other's thinking. When pupils talk about fractions with their peers, they are also will able to identify and correct misunderstandings naturally. The final principle is reflective thinking. After completing activities, pupils are encouraged to think back on what they have done and what they have learned. This reflection helps them making meaning from their experiences and strengthens long-term understanding. Okay, now I will explain the implications of a constructivist classroom and how this approach shapes the learning experience in our discovery stations. These implications reflect the ideas of constructivist thinkers such as Vygotsky who emphasize active learning, collaboration, and learning independence. First, we begin with hands-on learning. At this stage, pupils use manipulatives to explore fractions and build their own mental models. Before moving to abstract, by teaching moving and comparing objects, pupils gain a concrete understanding before moving to more abstract ideas. Next is inquiry. Instead of memorizing answers, people are encouraged to solve problems and ask questions like what happened if or why is the same, why is this the same. This inquiry-based process helps people think critically and develop deeper understanding. Okay. The third implication is collaboration. Learning does not happen in isolation. Through group work at stations, people share ideas, explain their thinking, and challenge one another's understanding. This interaction supports communication skills and reflects the needs of 21st century classroom. Then comes autonomy. At this stage, people begin to take ownership of their learning. They make decisions, test ideas independently, and gain confidence on their own abilities. This sense of independence is a key outcome of constructivist learning. Finally, assessment is carried out through a meaningful task rather than just written quizzes. We assess pupils based on how well they apply fraction concepts in real life or practical situation, which gives a more accurate picture of their understanding.
Now, let us move on to the next practical implementation of our lesson, starting with station 1, which we call the pizza parlor. This station is designed specifically for the enactive stage of Jerome Bruner's theory, where learning happens through physical action and direct manipulation of objects. At this stage, our main aim is to allow year 3 pupils to learn fraction by doing rather than by listening or memorizing. That is why this station focuses on hands-on experience using concrete materials. For this activity, pupils are provided with play-doughs, plastic knife, and physical fraction circle. The task is presented as a familiar and meaningful situation, which is sharing a pizza. This helps pupils relate mathematical ideas to real-life experience. The activity begins with pupils cutting a play-doh circle into half part. They take one pieces to represent half. Next, pupils take another play-doh circle of the same size, but this time they cut it into 4 equal pieces. This is where the discovery challenge takes place. Pupils are asked to find out how many of the smaller pieces are needed to match the size of the one-half piece. By stacking and comparing the piece, pupils discovering on their own that 2 out of 4 pieces are equal to one-half. To strengthen this understanding, pupils repeated the same process using fraction circle manipulative. They explore other examples such as 1/3 and 2/6 using the same hands-on comparison method. By the end of this session, pupils develop a strong concrete and spatial understanding of equivalent fraction. They are not just seeing numbers on paper, but physically experiencing that different slices can represent the same amount of pizza. This solid foundation prepares them well for the next stage of learning. That concludes session 1, the pizza parlor. Now, we move on to station 2, which is the art studio. This station represents the iconic stage in the learning progression proposed by Jerome Bruner. At this stage, learning shifts from physical manipulation to visual understanding, where pupils process ideas through image, diagram, and models. After working with concrete materials in the previous session, our aim here is to help year 3 pupils form strong mental image of equivalent fraction. Instead of touching object, pupils now learn by seeing and interpreting visual representation. For this activity, pupils are provided with graph paper, color marker, and picture card that display different fractions using shaded shapes. To guide their thinking, we use a visible thinking routine called I see, I think, I wonder. First, pupils observe the pictures card carefully. For example, they may see a rectangle with 1 out of 3 parts shaded placed next to another rectangle with 2 out of 6 parts shaded. Next, pupils engage in discussion with their peers. They talk about what they see in the shapes, what they think the shaded areas represent, and what they wonder about the relationship between these two fractions. This discussion encourages them to think critically rather than jump straight to an answer. Through this process, pupils begin to internalize the idea that although the fraction look different in numbers, the shaded area or value is actually the same. It is a key moment of conceptual understanding. To strengthen this iconic learning, pupils then move to the correction phase. Using graph paper and marker, they draw their own visual models of equivalent fraction by shading equals area in different ways. By the end of this session, pupils no longer rely on physical objects like pizza slice. Instead, they develop a clear visual and mental image of how equivalent fraction work. This visual foundation is essential before pupils are introduced to abstract symbol and equation in the next stage. That is conclude stage 2, the art studio.
Okay, now we move on to our final station, station 3, which we call the mathematician desk. This station represents the symbolic stage in Jerome Bruner's model, which is the highest level of representation. At this stage, pupils are likely to work with abstract symbols such as number, fractions, and equations. After experiencing learning through hands-on material in station 1 and visual method in station 2, pupils now have a strong conceptual foundation. This allows them to make sense of mathematical symbols meaningfully rather than seeing them as random numbers. For this activity, pupils are provided with whiteboards and markers. The lesson begins with pattern recognition. Pupils look back at what they discovered earlier, but this time the ideas are written purely in symbolic form. For example, 1 half is equal to 2 over 4. Next comes the discovery moment. Instead of giving pupils direct formula, the teacher poses a guiding question such as what operation can you apply to both numerator and denominator to get an equivalent fraction. This encourages pupils to think deeply about the relationships between the numbers. In line with constructivist principles, pupils then work together to deduce the rule on their own. They discuss these ideas and gradually realize that multiplying or dividing both the numerator and denominator by the same number produce an equivalent fraction. Once pupils believe they have found the rule, they apply it to a new challenge. For example, they are asked to find the equivalent fraction for 1 over 4 with a denominator of 8. They test their reasoning and check whether the rule still works. By the end of this situation, mathematical symbols are no longer just marked on a whiteboard. They become meaningful representation of ideas that pupils have already explored and understand through experience. That concludes session 3, the mathematician there. To conclude the lesson, we move into the closure phase, which we call as presentations. This phase strongly reflects the social interaction principle in constructivist learning. As emphasized by theories like Vygotsky, during this session, each group is given the opportunity to share their findings verbally with the whole class. They are required to explain the mathematical rule they discovered and support it with at least one visual model. This process allows the class to verify understanding and reinforces correct concept through explanation. At the same time, this presentation stage encourages reflections. Pupils look back at what they did, what they observed, and how they arrived at their conclusions. Through peer-to-peer discussion, they clarify ideas and strengthen their understanding. By the end of this learning journey, people have progressed from doing to seeing and finally to calculating. This ensures a holistic and meaningful understanding of equivalent fractions.
Now, to justify our teaching approach, let us look at how our discovery session align with Bruner's learning theory. It is important to emphasize that these activities are not random tasks. They are carefully designed to follow the 3 stages of representation proposed by Jerome Bruner. These designs scaffold learning in a structured way, making sure that abstract mathematical concepts are always connected to real experience. We can divide this into 3 distinct phases. First, the inactive stage at station 1. Here, pupils begin their cognitive journey by physically manipulating objects. They cut and stack playdough circle and use fraction manipulative. This is not mere play, it builds concrete spatial understanding and muscle memory of proportion before any symbols and formulas are introduced. Second, the iconic stage at station 2. At this point, pupils shift from touching objects to interpreting visual models. They draw shape on graph paper and shade areas to represent fraction. Now they are seeing the mathematics rather than just feeling it, which helps them visualize equivalent between different fractions. Finally, the symbolic stage at station 3. Once pupils have understood fraction concretely and visually, they move to abstract symbols and equations. Here, they discover for themselves the rule of multiplying or dividing the numerator and denominator to find equivalent fraction. Mathematical symbols now have meaning, grounded in the experience they have already explored. By carefully following this enactive, iconic, symbolic progression, we create a bridge from the real world to the abstract world of mathematics. This ensures that year 3 pupils gain a deep, meaningful, and lasting understanding of equivalent fraction.
To conclude our pedagogical justification, I would like to explain how this activity aligns with constructivist theory. In a traditional classroom, the teacher might simply stand in front and give a shortcut. For example, to find an equivalent fraction, just multiply the numerator and denominator by the same number. And students may copy the method, but they might not truly understand why it works. This is what we call a more passive spoon-feeding approach. However, our activity moves away from that method. Instead of directly giving the formula, we allow students to construct the knowledge by themselves. We carefully design a cognitive learning path, first at station 1 and station 2. Students experience the physical reality of equivalent fractions through hands-on activities. They manipulate, observe, and compare. At this stage, they build concrete understanding. Then, at stage 3, they move towards abstract thinking. Based on what they have observed earlier, they deduce the rule on their own because they discover the why before the how. The learning becomes deeper and more meaningful. It is not memorization, it is understanding. Furthermore, by using the rotating strategy, our activity strongly reflects social constructivism, especially Vygotsky theory. This can be seen in three aspects. First, negotiating meaning. Students discuss, explain, and sometimes even debate their ideas instead of working silently. Second, peer correction. During the I think, I wonder discussions, students naturally clarify and correct each other's misunderstanding, reducing the need for constant teacher intervention. Third, collaborative knowledge building. They work together to construct the fundamental concept, so the aha moment becomes a shared success. To sum up, we are not just teaching fractions, we are teaching students how to think critically, how to collaborate effectively, and how to become independent learners.
Now, I would like to explain the expected learning outcome of our Discovery Station design. We have organized the outcome into three main areas. First, mathematical understanding. Our main objective is for students to understand that fractions may look different with different numerator and denominators, but still represent the same value or the same proportion of a whole. More importantly, we want them to truly understand the reason behind the rule for equivalent fraction. Instead of memorizing that we multiply the top and bottom by the same numbers, students will know why this method works. This moves learning from rote memorization to meaningful conceptual understanding. Okay, second, skill development. Through this activity, students do not only learn theory, they also develop practical skill. They build spatial and hands-on skills when modeling fraction using concrete materials such as manipulative and playdough. At the symbolic stage, we strengthen their procedural skill by generating equivalent fraction using multiplication or division correctly. In addition, their communication skills are enhanced. During the final sharing session, students are required to explain their reasoning clearly to their peers. This builds confidence and mathematical language proficiency. Third is engagement in learning. This activity is intentionally designed to move away from passive worksheet-based learning. By using rotation station and incorporating physical movement, we engage kinesthetic learners. Visual tools support visual learners, while group discussion support interpersonal learners. These student-centered approach increase intrinsic motivation and curiosity. Our year 3 students will feel a sense of ownership because they discover the concept themselves rather than simply receiving it from the teachers. In summary, this design ensures that learning is not something that merely happens to the student, but something actively constructed by the students.
You have aligned Station 3, the mathematician dash with Bruner's symbolic stage, where pupils are expecting to deduct the rule of multiplying or dividing both the numerator and denominator to obtain equivalent fraction. At the same time, you emphasize moving away from spoon feeding or giving shortcuts. So, the concern is this. If a group of year 3 pupils who are still transitioning cognitively from visual to abstract thinking are unable to recognize the numerical pattern between 1/2 and 2/4, how does teachers support their discovery without directly telling them the rule? And then, at what point does guided learning become direct instruction, which you have positioned yourself against?
Thank you for your question, and here is my answer. The discovery process in Station 3 is not left to change, nor is it an abrupt shift into abstract thinking. Instead, it is a carefully structured progression that is intentionally designed to support pupils who are transitioning from visual to symbolic understanding. Firstly, pupils do not encounter abstract symbols in isolation. Before reaching the mathematician desk, they have already developed strong foundation understanding through the enactive and iconic stage. Through hands-on manipulation and visual representation, pupils build what can be described as a form of muscle memory for proportion and equivalent relationship. As a result, the symbols they encounter later are not unfamiliar ideas, but meaningful representation of experience they have already mastered. Secondly, the teacher's role at this stage is strategic, facilitation rather than direct instruction. Discovery is guided through carefully planned questioning, not by giving formulas or shortcuts. For example, instead of stating the rule, the teachers may ask pupils what operation can be applied to both the numerator and the denominator to maintain the same value. This approach narrows their focus and support reasoning, while still allowing pupils to arrive at the conclusion themselves. In addition, the transition from concrete to abstract is supported through pattern recognition. Pupils are encouraged to refer back to known examples such as recognizing that 1/2 is equivalent to 2/4 and then express this familiar relationship in numerical form. By translating what they already know into symbols, the abstraction becomes more accessible and less intimidating. Finally, once a rule is proposed, pupils are required to test their reasoning immediately using a new example, such as finding an equivalent fraction for 1/4 with a denominator of 8. This step is crucial because it distinguishes genuine understanding from guesswork. If pupils can apply the rule accurately in new contexts, it demonstrates that the discovery was meaningful rather than memorized. In this way, guiding does not cross into direct instruction. The teacher support the thinking process without removing the cognitive effort from the pupils, ensuring that discovery remain authentic, structured, and developmentally appropriate. Thank you.
Your justification for using rotating station is strongly based on social constructivism, where you describe the aha moment as a shared success and emphasize that pupils learn from one another. The concern is in a collaborative group setting at this station, how you practically ensure and access that every individual pupils has achieved learning standard 312, which is stating equivalent fraction up to denominator 10, since you have deliberately move away from written quizzes in favor of meaningful tasks and group presentation. How do you prevent social loafing, where one or two dominant pupils do the main discovery while others merely follow along without fully understanding?
Okay, although the lesson strongly emphasizes collaboration, their instructional design deliberately includes multiple layers of accountability to ensure that every pupil achieves learning standard 3.1.2, which is stating equivalent fractions up to denominator 10. Okay, firstly, individual thinking is made visible throughout the learning process. At Station 3, pupils use mini whiteboards to record the patterns they observe and the operations they apply. This strategy allows the teacher to circulate actively during lessons and visually verify each pupil's contribution and understanding rather than relying solely on a group outcome. Secondly, peer-to-peer monitoring plays an important role in maintaining individual accountability. Through structured social interaction and the negation of meaning, pupils are encouraged to question, clarify, and correct one another's thinking. This natural pre-correction process acts as initial layer of assessment, as pupils who are less engaged are prompted by their peers to explain their reasoning instead of passively follow along. Thirdly, accountability is reinforced through verbal justification. During the final presentation phase, groups are required to explain their reasoning and clearly and support it with a visual model. This allows the teacher to verify understanding across the group and to identify any individual pupil who may struggle to articulate the concept, even if the final group's answer is correct. Finally, assessment is carried out through performance-based and meaningful tasks rather than written quizzes. Pupils are required to apply the understanding of equivalent fractions to practical situation during the institution rotation, because each pupil must actively model, calculate, and explain fractions with this task. They are required to take ownership of their learning. This enables the teacher to assess competency based on observable application and reasoning, not just merely participation. In conclusion, while learning is collaborative in nature, individual understanding is continuously monitored and assessed through visible thinking, peer interaction, verbal explanation, and meaningful task performance. This ensures that shared success does not come at the expense of individual mastery. Thank you so much. Okay, to conclude our presentations, we would like to emphasize that meaningful mathematics learning happens when students are actively involved in discovering concepts, not when they are simply memorizing rules. We believe that when we shift the focus from what to think to how to find out, we are actually building more resilient and independent learners. Students are not just receiving information, they are exploring, questioning, and constructing their own understanding. Our approach is successful because of two main factors. First, the integration of theory. This lesson design carefully follows Bruner's strategy of representation, starting from concrete experience, moving to visual representation, and finally to abstract symbols. At the same time, it applies the constructivist principles where students actively build knowledge through experience and discussion. So we are not just teaching equivalent fractions as a topic, but we are following a proven psychological pathway of how students naturally learn best. Second, the holistic learning experience. By combining hands-on activities, visual models, and collaborative group discussion, we ensure that students develop more than just computational skills. They strengthen their mathematical reasoning, at the same improve their communication skill, and build confidence in expressing their ideas. At the same time, the active and interactive nature of the lesson promotes positive engagement towards learning mathematics. In the long term, these elements are what make learning effective, meaningful, and sustainable. Our hope is that through these discovery stations, our Year 3 students will not only master equivalent fractions, but also develop a curiosity and a positive attitude towards mathematics. With that, we conclude our presentation. Thank you very much for your attention.